Hello and good afternoon, everyone. I hope I am audible and visible to all of you. Can you hear me? Jayant, Vishnu, Gojraju, am I audible and visible? Okay, great. So this class took some time. I was there in the class. No one came. I thought because of Ganesh Chaturthi. By the way, wishing you all a very happy Ganesh Chaturthi. I hope you are enjoying your festive time. We'll try to wind up this topic of capacitance today in this class. What we have done up till now, we have seen what are the different types of capacitors and what happens when dielectric is inserted in the capacitor, series and parallel combination. We have not done question on series and parallel combination because we'll be doing it in the chapter electric current. So in electric current, when we solve resistances for series and parallel, that will be same as solving capacitances for series and parallel because the concept remains same. So we'll be doing that in that class. What we are going to do in this class is something which I don't know if you have seen or not, but this is what we are supposed to do in today's class, that is known as the force on a dielectric inside a capacitor. Force on a dielectric inside a capacitor. Whenever we put a dielectric inside a capacitor, what is the force acting on the dielectric? Remember, if the dielectric is completely inside, as in this case, the dielectric is completely inside, if the dielectric is completely inside, the force on the dielectric by the capacitor plates is 0. So remember that when the capacitor, when dielectric comes, remember we are talking about a solid dielectric here. In case of liquid dielectrics, situation becomes a bit more confusing. There was a question in SC Verma that I would ask you to solve it, the solved example. We are talking about liquid dielectrics. The case is a little bit different. Concept is same, but the application you will have to understand it in a better way. We're talking about solid dielectrics here. When the solid dielectric is completely inside the capacitor plate, the force on it becomes 0. Do we understand this? Now, if it is not completely inside, if it is not completely inside, say some portion of it is inside and some portion of it is outside, you can see this plate of the capacitor is positively charged and this side of the dielectric becomes negatively charged. So this dielectric is actually pulled inside the capacitor plates. This dielectric is actually pulled inside the capacitor plate. This is the negative plate of the capacitor and this is the positive induced charge on the dielectric. We know that the charges induced on the dielectric are opposite to the charge on the capacitor plates. So this dielectric is pulled inside this capacitor. Now this can happen in two ways. What are the two ways in which this can happen? The first way in which this can happen is by keeping the voltage source connected. That means I am keeping this capacitor plates connected with a battery. Now, if I connect it with a battery, if I connect the capacitor plates by a battery, the potential difference between the capacitor plates is kept constant. In that case, what happens is we are supposed to find out the force which is pulling this this dielectric inside the capacitor plate. How do we find out this force? We find out the energy of the capacitor at any point in time. It is half CV square. Force, this is the conservative force, so it is minus du by dx. Minus only indicates that it is getting pulled. So if you integrate this, v is constant, so v square by 2 comes out. It is integral of it is the derivative of dc by dx. So this force becomes v square by 2 into dc by dx. You can find out this value. You should be able to find out the force acting on the capacitor if, remember, the condition here is voltage is constant. Do we understand this? Can I have some raise hand that we understand this? So voltage is constant. This is the formula. Now in this case, in this particular case, what will be the force acting on the capacitor? As you can see, in this case, X length of the dielectric has come inside the capacitor. The total length of the dielectric or the capacitor plate is L. Total length of the plate is L, and X part of it has come. So now it can be broken up into two capacitors, C1 and C2. C1 is the space which does not have the dielectric. C2 is the space which has the dielectric. We can find the effective capacitance as it is done here. We can find the effective capacitance as it is done here. This is the capacitance of the part which is filled with the dielectric. It is multiplied by K. This is the part C1 which is not filled with the dielectric. These two are in series combination. So we find out the effective capacitance, and then we can find out the force acting on this capacitance. Force acting on this dielectric by finding out dc by dx and multiplying it by v square by 2, and that is done here. This entire thing is dc by dx. You multiply it by v square by 2. This is a constant force that is coming. The formula is epsilon naught b. B is the width of the capacitor plates. K minus 1 v square by 2d. Do you understand this? This is how you can find out the force acting on a dielectric while it is inserted inside the capacitor when the potential difference of the capacitor is kept constant. In the second case, what is going to happen is we are going to keep the charge on the capacitor constant. That means we are going to charge the capacitor and we are going to disconnect the battery, so the charge on the capacitor remains constant. X part of this has come inside. L minus X is the part which is remaining. We find the capacitance of this system. This is the capacitance of the system. Now we use the formula for energy as Q square by 2C, because Q is constant. Now we differentiate this du by dx. So we differentiate this with respect to x, and this will be the formula that we will get. If I differentiate this with respect to x, the force in this case will be given by this formula, Q square by 2C square dc by dx. You once again find the value of dc by dx. dc by dx is given by this formula. You put the value of dc by dx here. You should be able to get the force on the capacitor when the charge on the capacitor is constant. Do we understand this? Am I clear with what we have discussed here? Can I have some raised hand that we understand this, sir? We have discussed how to find the force acting on the dielectric, on a solid dielectric, when a solid dielectric is inserted into the capacitor plate. Remember, the force always tries to pull it. There are some questions in SC Verma where you have to find if this motion is very slow or this motion is very small. You have to prove that it is simple harmonic in nature. You need to find the time period of that. That are the question given in SC Verma. I hope you would be able to solve them with this phenomena. Let me move ahead and get to the point where we are going to discuss charging and discharging of a capacitor. What do you mean by charging and discharging of a capacitor? What do you mean by charging? Charging means when this capacitor is connected to a battery, and as soon as you put the switch on, in this case to position number 1, what will happen? Charge on the capacitor will slowly begin to rise. During this period, the charge on the capacitor will keep on changing continuously. Though this process happens very quickly, but during this time, the charge on the capacitor keeps on changing, and sometimes it is also known as transient state. Transient state means this is the state which is continuously in transit. This is the state which is continuously changing. The charge on the capacitor when the charge on the capacitor as a function of time, if it is uncharged initially, is given by this equation. Q is equal to Q naught 1 minus e to the power minus t by RC. This is the formula that you can apply if initially it is uncharged and you are supposed to find out charge as a function of time. This Q naught is the maximum possible charge. This Q naught is the charge at infinity. What do you mean by infinity? After a very long time, what charge this capacitor gets is known as charge at infinity. And that will be, if you all know it, you must be knowing it, that value of Q naught will be C multiplied by V or C multiplied by E. Actually, in theory, this capacitor never gets charged. It takes infinite time to get charged, but we can assume that after some time, maybe even a millisecond or a second, you should be able to completely charge the capacitor. Then there is something known as RC, which is known as the time constant of this charging circuit. It is the time taken by the capacitor to go from zero charge, from 0 to 63% of the maximum value. Whatever time it takes, that is known as the time constant of this charging circuit. Do we understand this, everyone? I hope you know this. Time constant of a capacitor. Now, if someone asks you what is the voltage difference across the capacitor, you can use this formula. The voltage difference across the capacitor as a function of time will be V naught into 1 minus e to the power minus t by RC. As soon as you multiply this V with C, you will get the value of charge on the capacitor at any point in time. If someone asks you to find out the current in the capacitor, so what do? You have the value of charge Q is equal to Q naught into 1 minus e to the power minus t by tau. You differentiate this equation with respect to time. You differentiate this respect to time. Whatever you get will be the current in the capacitor as a function of time, and it will be equal to I is equal to I naught e to the power minus t by RC. I will be equal to I naught e to the power minus t by RC, or I can write it as tau I naught. What is I naught? I naught is the current in the initial condition. Now, as you can see, if I put the value of time as 0 seconds, I becomes equal to I naught. If I put the value of time as infinity, I becomes 0. This is how current changes from maximum to 0 it becomes. While the capacitor is connected, as soon as the capacitor is connected, current is maximum, charge is 0. As the capacitor keeps on charging, charge decreases, but current charge increases, but current decreases. When the capacitor becomes fully charged, the current in the circuit becomes 0. So if I have to call capacitor as a resistance, someone told me that it is the inverse of resistance. Now, if I have to call capacitor as a resistance, how will I equate it to a resistance? How will I equate it to a resistance? I will call capacitor as a variable resistor. I will call capacitor as a variable resistor. Why will I call it as a variable resistor? Because its resistance varies. Its resistance varies. How does its resistance vary? At time t is equal to 0, the resistance of this capacitor, let me call it as RC, the resistance of this capacitor is 0. That implies current is maximum, which is I naught, which is E divided by R, where E is the battery and R is the resistance of the circuit. At time t is equal to infinity, when the capacitor becomes fully charged, here you must remember that the charge on the capacitor is 0. At time t is equal to infinity, charge on the capacitor becomes Q naught, that is the maximum possible value. That makes the resistance of capacitor almost as infinity. And current in the circuit becomes 0. So basically, it behaves like an open circuit. The capacitor behaves like an open circuit. At t is equal to infinity, capacitor behaves like an open circuit. If I say the capacitor behaves as open circuit at t is equal to infinity, how does the capacitor behave at t is equal to 0? At t is equal to 0, current is maximum, capacitor behaves as 0 resistance, resistance is 0. I can call it as capacitor behaves as a short circuit. Capacitor behaves as a short circuit. In between this short circuit and open circuit, between 0 to infinity, how does the charge on the capacitor change? How does the charge on the capacitor change? Q is equal to Q naught into 1 minus e to the power minus t by tau. Do we understand this? It has gone way above our heads and I have gone too fast. Do we understand this? Yes or no? Can I have some raise hand that we understand this, sir? Okay. Now, there might be questions based on this phenomena. Okay, we have understood how the capacitor discharge, how the capacitor charges. Let us also try to understand, and then we will go into the questions straight away. Let us try to understand how the capacitor discharges. How does the capacitor discharge? Now, to discharge the capacitor, you must understand that first we need to charge it. Without charging the capacitor, we cannot discharge it. So first we need to charge it. How will we charge this? We will charge this by the original circuit. Here is the original circuit, as you can see. Here is the original circuit. For charging, we will put the key to position number 1 and keep it in this position for a very long time. So once we keep it at point 1 for a very long time, this capacitor becomes completely charged. If this is the positive terminal, this will be the positive terminal for this capacitor. This will be the negative terminal of this capacitor. After a very long time, charge on this capacitor will become Q, which is equal to Q naught, which is equal to C multiplied by E. Do we all agree on this? Can I have some raise hand that we agree on this, sir? After a very long time, we keep this circuit connected to point 1, the charge on the capacitor will reach its maximum value Q naught. Now, as soon as it reaches its maximum value Q naught, we will disconnect the connection and then we will make this blue connection. This blue connection means I am connecting it to point T, point 2, and again I am starting the time as T is equal to 0. And again I am starting the time as T is equal to 0. So now what I have done is I have charged the capacitor first and then I have connected it to an external resistance. Capacitor being fully charged, I have connected it to an external resistance and now I am going to discharge the capacitor. How will I discharge the capacitor? By connecting it to an external circuit, I can discharge the capacitor. What will be the value of charge on the capacitor as a function of time? That is what we need to calculate. And how will you calculate it? So here is the circuit once again. First we connect it to point A, charge it completely. Then I switch to point 2 and start the time t is equal to 0. How does it get discharged? Q is equal to Q naught e to the power minus t by tau, where Q naught is the charge initially on the capacitor. In this case, the charge is C into E, and this is how the capacitor gets discharged. As you can see, for maximum value, after a very long time, infinity, the charge on the capacitor will become 0. Here also we have something known as the time constant, which is now the time constant of the discharging circuit. Now, what is the time constant of the discharging circuit? Everyone should know that this is the time taken by the charge on the capacitor. The charge begins from Q naught and gets into 37 times or 37% of that Q naught, whatever time it takes, that time is known as the time constant. Remember the dimensions of R and C. R multiplied by C is the inverse of time. The potential difference can be calculated. The current can also be calculated by the derivative of the charge of the capacitor. We are not going to go into how we are getting the equation for this, because there is no point of doing that. Do we understand this? Charging and discharging of the capacitor. Now we'll try to solve one or two questions and we will see how we can apply these concepts and do questions. Now, what we have seen is, in the question, what we saw was the charging and the discharging time constant were same because the same resistance was kept there. This might not be the case always. This might not be the case always. So what do you do is that you find out what is the charging and the discharging time constant in different ways. Now what I'm going to do is I'm going to draw a diagram and we are going to solve all the possible questions that can be made in this. Please listen to me very carefully. We call it as R2. Let me call this as C. Okay, so this is my circuit. This is the distance R1. This is battery E. And there is a switch. Now, how does the question begin? The first part of the question is, at time t is equal to 0, switch is switched on. Switch is on. Now, what I'm going to do is I'm going to draw three currents, I1, I2, and IC. I1 is the current through the branch of R1, I2 is the current through the branch of I2, and IC is the current through the branch of capacitor. My question here is simply, at time t is equal to 0, what is the value of I1, what is the value of I2, and what is the value of IC? Can you tell me this? It gives you a minute. At time t is equal to 0, switch is switched on. What is the value of I1, I2, and IC? Anyone can tell me this answer? Okay, I will help you out. Now, how do I solve it? As soon as I see that time is 0 and switch is switched on, that means as soon as I put the switch on, how does this capacitor behave? At time is 0, how does this capacitor behave? The branch of this capacitor in which this capacitor is there behaves like open circuit. It behaves like open circuit. If it behaves like open circuit, then what will happen? No current will go in this branch. So my IC becomes 0 because it behaves like open circuit. Now if IC becomes 0, I1 and I2 both become same, and it is easy to understand what is the value of I1 and what is the value of I2. I1 and I2 both are same, and both value will be E divided by R1 plus R2. So that becomes my first answer. Do we understand this? How did I get this? At time t is equal to 0, how did I find out the value of I1, I2, and IC? Can I have some raised hand that we understand this, sir? Have I done a mistake? At time t is equal to 0, I am calling it as open circuit. Is it an open circuit or is it a closed circuit? What did I tell you? Look back. What did I tell you? When time is 0, remember, you might get confused between a capacitor and an inductor, because an inductor reversing happens. At time t is equal to 0, resistance is 0, and the capacitor behaves like a short circuit, not as open circuit. So whatever I have done is not time t is equal to 0. Whatever I have done is for time infinity. After a very, very long time, what happens? After a very, very long time, the distance of the capacitor becomes infinity. At time infinity, the distance becomes infinity and it starts to behave like an open circuit. Remember, do not make a mistake. In inductor, the reverse happens. In inductor, at time t is equal to 0, it behaves as open circuit, and at time t is equal to infinity, it behaves as short circuit. Will you remember this? I made this mistake knowingly, so that you understand that you can also make the same mistake between capacitor and inductor, because the same question can be asked for an inductor. Can you please raise hands and tell me, sir, you have understood this, how I have done this? And the main point was, remember, t is equal to 0 and t is equal to infinity. What is the difference? Now let us go to the point where t is equal to 0. At t is equal to 0, as soon as the switch is switched on, what is the value of I1, I2, and IC? Now we'll try to do it by the blue one. Now remember, at t is equal to 0, if you are getting confused, just write this capacitor behaves like short circuit. This capacitor behaves like short circuit. Here you can write, remember, this capacitor behaves like open circuit. No current goes in the capacitor. Now, in this case, capacitor becomes like a short circuit. So basically, this circuit is shorted. This is the blue one. The circuit is shorted. As soon as the circuit is shorted, nothing goes in the above branch, because there is no resistance in this branch. So as soon as the circuit is shorted, I2 becomes 0, I1 becomes equal to IC, and the value is E by R1. Do we understand this? Can I have some raised hand that we understand this? You understand this? Okay, great. Now, let me change the question, because I might not get enough time in inductor, and let me put an inductor in case of this, so that you understand the difference between the two questions. Let me put an inductor here now. I hope you know what is an inductor, right? Do we know what is an inductor? Now let me put an inductor here. Same question, same phenomena. Switch is switched on. This is I1, this is I2, and this is IL. Now, let me solve this question for an inductor. Let me put the same question for inductor. And the question is, at time t is equal to 0, what is the value of I1? What is the value of I2? What is the value of IL? Can you tell me? I've told you enough about this. At time t is equal to 0 for an inductor, what happens? Anyone can tell me, or shall I do it? Remember, for inductor at time t is equal to 0, capacitor at time t is equal to 0 behaves like a short circuit. Inductor at time t is equal to 0 behaves like an open circuit. Remember this. So the case gets reversed. Now this becomes an open circuit. No current goes here. So whatever was answer I was getting for infinity, the same answer I'll get here. Here IL will be equal to 0 and I1 will be equal to I2 will be equal to E divided by R1 plus R. Will you remember this always? What happens at t is equal to infinity? At t is equal to infinity, inductor behaves like a short circuit. Inductor behaves like a short circuit, so this branch gets shorted. So whatever was happening here at t is equal to 0, now happening here at t is equal to infinity. Inductor becomes shorted, so my I2 becomes 0, IL becomes equal to I1 becomes equal to E by R. Do we understand this? When I have some raised hand that we understand this, sir. Between infinity and zero, between zero and infinity, what difference does it make? For capacitor, inductor, someone told me that no, capacitor is the inverse of resistance. It's better to say capacitor is in some ways inverse of inductance, because what inductor is doing, capacitor is doing exactly the opposite of it, as you can see here. Are you getting my point, bacha? Vishnu, Jayant, are you getting my point, everyone? If you have to call the inverse of inductor as inverse of capacitor as something, the better option is an inductor rather than a resistance, because inductor and resistance and capacitance are all linked to each other. How they are linked to each other? Let us say, for example, I take the series combination. I take the series combination of all this. Resistance in series will be summation of Ri. I hope you understand the meaning of this term. Inductance in series will again be the summation of Li. So they are going on the same track. They are going on the same track. But if I say for capacitance, 1 by capacitance will be summation of 1 by Ci. So this becomes inverse of it. Okay. Now if I go on parallel combination, things become different. 1 by Rs is summation of 1 by Ri. 1 by LP बोलना चाहिए. LP 1 by LP is summation of 1 by Li, and capacitance in parallel is equal to summation of Ci. Do we understand this? So whatever resistance does, inductor behaves in the same way. Are you getting me? Everyone getting me? Right? So this is the way you can remember all in the same way. Again, go and I'll tell you. You can draw a table like this. I have told you series and parallel combination. I'll tell you one more thing, so that this L, R, and C all are done together. First is R, second is C, third is L. What I'm going to do here is I'm going to write some stuff. Okay. What is the first formula? Now the first formula, if I write here, formula, let me write voltage. Voltage. How is voltage calculated? How is voltage calculated here? V is equal to IR is the formula here. You see V, you see I, you see R. V is equal to Q by C. So you understand the difference. V is here. V is here. The place of R has been taken by 1 by C, and the place of current has been taken by the charge. And that is how things pan out everywhere. Now for hit this one, V is equal to minus L di by dt. R has been replaced by L, and I has been replaced by minus L minus di by dt. Do we understand this? So basically, whatever part current is playing in resistance, the same part charge is playing in capacitance, and di by dt or I is playing in inductance. Do we understand this? Do we understand what I'm trying to say? If I talk about energies, if I talk about the power or energy, heat energy dissipated, heat energy, the formula is I square R into T, I square R. Remember, यहाँ पे energy stored in the capacitor, if I write in the same formula, it will be Q square by 2C. I की जगह Q, R की जगह in the denominator C, and for time I have half. Energy, this is electrical energy. Energy will be stored in the form of magnetic energy in an inductor, and the corresponding formula is half L I square. Half is from here. L takes the place of R, and I square for I square. So this is how column wise you can understand. If you understand one, you should be able to understand all. Remember what to remember. This L and C are sort of reciprocal of each other. Whatever C does, L does the reverse of it. At time t is equal to 0, capacitor behaves as open circuit, inductor behaves as capacitor behaves as short circuit, inductor behaves as open circuit. At time t is equal to infinity, capacitor behaves as open circuit, but inductor behaves as short circuit. Now, wherever in a question you find capacitor is in steady state, whatever question you find, you are supposed to find out the charge on the capacitor in steady state. How do you find the charge on the capacitor in steady state? Let me see if I have a question here. How do you find the charge on the capacitor in steady state? Do you know? You might have questions where you will have a combination. You will have a combination of resistances and capacitance, and then they will ask you to find out the charge on the capacitor in steady state. In that case, what do you do? I'm not able to find it here. Forget about this. I'll make a question. You are supposed to find the charge on this capacitor in steady state. For example, this is R, and this is C. This is E. Now you are asked to find the charge on the capacitor in steady state. Now, how do you find the charge on the capacitor in steady state? To find the charge on the capacitor in steady state, you have to assume that this has become open circuit. This goes away. Now, once this goes away, you find the potential difference between these 2 points. You find the potential difference between these 2 points, which will be the potential difference across the plate of the capacitor. How do you find the potential difference across these 2 points? You find how much is current flowing in this branch, how much is current flowing in this branch. It is will be E divided by 2R. Then what will be the potential difference across these 2 points? That will be E by 2R multiplied by R. That is the potential difference across the plates of the capacitor multiplied by the capacitance C. The answer will be the charge on the capacitor in the steady state. No matter how complicated the question is, you just remove the branch in which the capacitor is kept. You find the potential difference across the branch of the capacitor multiplied by C. You should be able to get the charge on the capacitor in the steady state. Am I clear with these 2 points? Now, in the next class, we'll be beginning with resistance. We'll be solving electrical circuit, including resistance. I'll give you a very nice way of solving them. That is my own way of solving the circuits. That is known as a nodal theorem. I'll tell you more about nodal theorem. So I'll solve resistances with nodal theorem. And I will also solve capacitance circuit with nodal theorem. So don't miss the next class. That is going to be probably the most important class that you will ever have attended in this particular topic. So I'll see you there in the next class with this nodal theorem. And search on net what do you find about nodal theorem, and then you will see my tariqa of doing it. I hope you find it interesting. Chalo. On that note, I'll say bye bye. I think you have a second class coming up. So enjoy your class. Stay happy. Bye. If you have any doubts, you can ask me.